All right. Hey, everyone. I'm going to give a high-level introduction to ML. It used to be the case that you'd have to go from a sort of high-level description to maybe some math, and then there's another layer of translation from math to code. Luckily, we're now in the ChatGPT phase, so you can just look at the code on your own. It's quite simple now to go from math to code because you have this translation. Now, I don't, that's not to suggest that ChatGPT is the only way you should be doing coding, because if you don't know what you're doing, ChatGPT, of course, hallucinates. Any of these models hallucinate. So you have to certainly be sure that it's not doing something silly. And the interesting thing, and just as a side note, the interesting thing about the models is that they do something silly in a way that's hard to detect, and that's by design. And that actually speaks to the power of these models, which is that if you give them a goal, and I often have this joke that they're just like undergrads, if you give them a goal, they will find the least energy path to get to that goal. Oh, but you didn't say, like, shit, you're right, I didn't say that. So I have to give you credit. So that's kind of like these deep learning models in particular are like that. So we'll understand the principles of that as we go through this setup of how a machine learning problem is set up. And we'll see that, in particular for GPT models, they were specifically trained to give you answers that humans will like. And so when they produce an answer, it may have a very, very subtle bug, which is very hard to detect. And that's because, they're trained to print something out that you will like. So, be very careful when you use it. Okay, so let's take a 10,000-foot view on what ML is. Machine learning is, we're going to be quoting a bunch of famous people in ML. These slides are actually from UPenn's Intro to Machine Learning course. I thought they were very good. So Herbert Simon, one of the early machine learning researchers, said that learning is a process by which a system improves performance from experience. And so we start with this sort of high-level observation that what we'd really like is to provide experiences to a machine, and then for this machine to learn from the experience. So now, what that basically means that anytime you're doing any sort of science, you take a high-level observation and you start to crystallize it. You have to be more precise in what you're stating. I spend years teaching my PhD students to learn to do this, but it is one of the most important things you will do as an engineer and as a scientist. So you start off with this high-level statement. Tom Mitchell comes along and he's like, yeah, we love that statement, but what does that mean? Let's go one level deeper. Let's redefine it. Let's include some terms. And then we can talk about the specific concepts relative to these terms. We say machine learning is the study of algorithms that improves their performance, P, so we have to have some performance metric. What does it mean to improve? And there's a whole science behind designing methods and techniques to measure how well your model is doing. For some tasks, so we have to define the task. In many cases in machine learning, you're mapping X to Y, and you're finding some function that maps input X to output Y. And so that task is, defines what the inputs are, what the outputs are, and what the structure of the model will be. And this is, by the way, the case even in simple math when you're doing sort of regression, right, where you have your X and Y, and you have to fit a line. So you're immediately making a bunch of assumptions about that relationship, and you're making a very strong assumption about that line. You're saying it's linear. It must be linear, right? And so you're sort of immediately, implicitly baking in constraints into the model. And experience is E. So in the context of ML, that means samples. That means I give you a bunch of XY pairs, and you learn how to map one to the other. Okay, so the E is a set. The task is defined by the inputs and outputs and the structure of the model. And the way that the model is learning is P is getting better. Sometimes that means that when you're taking a measure, that value is going up. Sometimes it means it's going down, and it depends on how you've set up the optimization problem. Okay, so in other words, a learning task can be defined by this 3-tuple PT&E. Okay, so we're still relatively high level, but we can start to decompose a machine learning problem into these 3 main components. So far, so good? Great. Now, machine learning represents an inflection point in how we've thought about. Well, that seems cool, but also a little scary. I don't know what did all that. Okay, a little distracting. But anyway, so in traditional programming, we've thought about the way before ML is to think about, well, it works, whoever's running it, it works. You have some data that's coming in into the computer, and you have some output that you'd like to get. And you're gonna write a program that takes your data, runs on your data, and gives you the output. Right, and so that's like, if, then, else, function call, blah, 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 whatever your program structure is. And that's still not deprecated. You still have to think about it. There's still a part of the world, especially in software building, for big complex pieces of software where you think of the world this way. Okay, but machine learning, especially for much more tractable problems where it's like very well defined what you're passing into the model and what's coming out, the view has transformed to, I have some data and I know what I'd like to get, but I don't know how to write that program. So I will have the computer learn how to take the data and write the program that generates the program that maps the data to the output. Okay, and so what we're seeing again, when you're doing any sort of composite machine learning system design, we're still thinking like this in some parts of it, and also thinking like this in other parts. There are programs that are just really hard to write, and it's just much easier if you happen to have a lot of data to feed it and to generate that part of the program for you. But this is the sort of relationship between traditional programming and the way machine learning views the world. So if, as a programmer, and I assume everyone here knows how to program. Yes, okay. I'm gonna assume yes and not call it out. But when you're writing a program, you think, boy, I'd really like to write this thing that like writes to a file and takes an aggregate of a bunch of numbers in this file and what have you. And you sort of think through the logic. You think, how am I gonna scan through this data? I have to write to my file descriptor. You're like breaking it down into the individual components. In machine learning, every time you start a new machine learning problem, you say, well, I have some data, and this data presumably is labeled. Somehow I know the thing I want to get from this data. Now you think, what do I think is the relationship? What are the properties of the data that I'd like to extract? And that informs the structure of the model that you're going to feed this data and these labels to. And so that kind of thinking is a slight variation on how you think about writing programs, but it's the fundamental way in which you approach any machine learning problem. It's like, what's your data? What's your output? And what hypothesis am I making about the relationship between the data and output that's captured in the structure of the model? Okay, so when do we use ML? I'm very biased. I think we use it everywhere. Like almost every field uses ML. One way or another, at some point in the software stack, there's some version of ML. And I think machine learning and AI has had this kind of curse to it, where it used to be an AI problem, and when it's well solved, it's no longer called AI. So search is a problem. It was an AI problem in the 90s. And then Google came and kind of solved that. And so we just called it search. But it used to be like a fundamental AI problem. You know, there's a bunch of other examples like this, including playing chess and everything else, which are fundamental AI problems. Playing chess, that's simple now, right? We now do Go, and even Go is doing a lot, you know, has beaten the world's best at Go. So some places where ML might be used is where there's no human expertise. In which case we just have a lot of data and we're not sure what's there. We haven't experienced it. So we're trying to gather as much data as possible and extract any meaningful patterns from that data. If humans have a hard time explaining their expertise, so speech recognition is, I mean, I'm not a speech recognition person, but as far as I'm concerned, it's almost solved. Like I can pull up, particularly the OpenAI's speech model is so good that I just free form talk. And it almost never gets it wrong what I'm saying. Okay. When models have to be customized, we can use ML. We can use ML when we have huge amounts of data. You're typically bound by the amounts of data and compute that you have. So specifically in regimes where you have a lot of data and have a lot of compute, use it, right? Like use the data, use your compute. It's in situations like, now the question gets more murky when you maybe don't have a lot of data or don't have a lot of compute, where you have to do more of the computational engineering yourself, but you can still sort of siphon off parts of your model to answer the question and build this mapping between your inputs and outputs. You know, learning isn't always useful. So here's like learning to calculate payroll, where you're just adding things together. Sometimes, you know, especially when you're first introduced to machine learning, you're like, oh yeah, we'll just point it at everything. And, you know, it just doesn't always make sense for every problem. There, you know, one thing that you start to learn when you study some of the fundamental properties of the particular models that you happen to pick, that sometimes they just can't fit your data, especially when it's really simple. Right? So for instance, a neural network has a really hard time fitting waves. Okay. So a classic machine learning problem that was the benchmark for a few decades is this human handwritten digit recognition. I'm sure folks have heard of this or seen this. And you know, some of these are hard for humans. Like I can't tell that's a 7. This is chicken scratch. It's freaking nervous. This 3 is weird. This 3 is really weird. This is a sort of a classic example where it's hard, even for some humans, to pick up. Look at this too. It's a horrible too. Right? But you know, the key thing here was like, I can't write a computer program that generalizes very well from that. Right? So that's a classic situation in which machine learning is really the only way we know to solve it. I don't know the set of rules. I cannot produce the computer program that can identify all of these digits with practically 100% accuracy. I don't know the if-else statement of pixel reading that will solve that. So machine learning is the right answer there. Some more examples. Facial identities or facial expressions. Hard to write a computer program for that. Handwritten or spoken words. Medical images. We have generative AI. I'm sure everyone's heard of generative AI. Right? So anything that's sampling from a distribution and generating realistic samples. You know, ChatGPT, all the GPT models. Sora, I'm sure, how many folks have heard of Sora? So also from OpenAI, just producing these movies. Just a bunch of examples of generative AI these days, right? And that's an old concept. That's sampling from a distribution such that the output has the same structure as the distribution that it learned from the inputs. Recognizing anomalies is really important. Comes up in all sorts of practical applications. Credit card transactions, something looks weird, flag it. Sensor readings, right? Identifying anomalies in sensor readings. Nuclear power plant could be very important, knowing that your sensors are giving weird readings. And if you want to make a lot of money predicting the stock market, that's a very, very difficult problem for which there's no way you're going to compete with hedge funds on your own. But that's basically what they do all day, is like try to predict where the stock market's going to move. And the sample applications, these slides are from 10 years ago, and it was still quite large. It's probably even larger today. I often talk to people in various disciplines, and there's always sort of a computational analog to almost any field, right? Even like my wife studied literature, and there's computational literature, right? That exists as a field now. And so, people are applying machine learning to evaluate, to find patterns in literature and structures and stories, to do translation, to do automatic translation. There's people who are in computational law. Has anyone heard of computational law? There's computational law. There are companies that come out and build and use language models to understand whether a particular law applies in a certain situation. Right? You could argue that like search has already been part of law. Like that's how you search for cases. You have to have some kind of like internal search engine to go find potential cases that match the case that you happen to be dealing with now. Right? So this field is expanding. Another famous ML researcher, actually the guy who coined the term machine learning, said it's a field of study that gives computers the ability to learn without being explicitly programmed. Just harping on the same message. This guy built a self-learning program that learned how to play itself in checkers and get better over time at playing checkers. And this was back in the 50s, before there was, neural nets and everything else. There was a concept of neural nets, but not the computational infrastructure to carry it out, nor the data storage capacity either. But he made really good progress on this. From checkers went on to chess, from chess to Go. So then the question becomes, okay, all right. I get what machine learning is. So PTE, what are you talking about? How do we do that? Because anytime you start off with this sort of high level objective, I'm going to give you a problem and I'm going to say, okay, now define it. What does define it mean? Define means reduce it to PTE. That's one level of reduction. So I know what the problem is. I know what the task is. I know what your metric is. And I know what experiences you're going to feed to this thing. That's one level of reduction, which gets us one step closer to clearly defining what the problem is. Okay, so you come into a problem, any problem where you think you might need machine learning, you say, okay, well, if I'm playing checkers, well, that's the problem, that's the task. Playing checkers consists of a set of rules, blah, 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 whatever. Right, that defines T. I'll know if my model is doing well if over time I'm winning more games. Okay, well, what's a win? So you have to define a set of rules such that there's like an objective, and you're sort of moving towards that objective with each iteration. And the experiences in the case of checkers is the play itself. Recognizing handwritten words, high level, that's the task. The percentage of words that were classified correctly, so your accuracy, and a database of human labeled images and handwritten words. That's what you're going to need. What oftentimes happens in the internships that we host here is that we don't have E readily. Sensor data is really cheap and easy to produce. Getting labels, very hard, very expensive. That's still an open problem today. It's why you don't see more machine learning papers that are talking about sensors. They talk about vision, they talk about language. Yeah, those are easy to label. But okay, I have a time series that's measuring some vibration somewhere. I can't outsource that. I have to have lots of domain expertise to label that. And to label it at a scale to build foundation models is another challenge in and of itself. Driving on a 4-lane highway. So this comes up here. I know folks are looking at cars that have sensors on them and all the rest of it, right? So what's the task? Well, I'm going to tell the state of the world, and I'm going to have some control configuration. Like I can control the pedals, I can control the steering wheel, and I can control the brake. And there's 3 parameters that I can set, and they change the state of the world, and I use the sensors to observe how the control decision I'm making is, changing the state of my perception of the state of the world. And so here, you might have your experience to be steering around and looking at the state of the world. And for P, the metric, there's lots of metrics for self-driving cars. Primarily, don't hit something. Definitely don't hit someone. But at a high level, do well according to what a human thinks means doing well, right? So let's start with human judged error. Let's do this in simulation so that we make sure that we're not hitting people or things. And, you can generate a lot of examples in simulation, get it to the point where you can get it onto an actual vehicle. You're certainly not going to put it out in the street first. That's going to be the last place you put it because of the risk. You might have other metrics. You might have other P's, which are not human error, but maybe some equation that captures the level of risk associated with a move. And the level of risk could be a function of how close you are to the nearest object. Or you could say that the level of risk is related to the relative difference in speed between you and your next closest object. Right? Which is, by the way, why riding your bike on the highway is a bad idea. That there's a big difference in those 2 speeds. It's very risky. So that could be another measure that you're trying to optimize against. And the one I think almost no one thinks about anymore, because they've gotten so good, are spam detectors. This used to be the open problem 20 years ago. We used to get a lot of spam, and now it almost never happens. In fact, the thing you want to capture here is not just how many, you certainly want to capture the percentage of emails that get classified correctly, which means false positives have to be low too, particularly false positives, because it's okay for some spam to make it through, but it's really bad for a good email not to make it through. And there are tricks you can play with the math to set up the weights to penalize the model if it gets a false for every false positive. Right, so there's a bunch of things in the mathematical setup of the problem that allows you to sort of ding the model more or guide the model in the right direction. Okay. I'm prefacing this with the state of machine learning models in 2014. Okay, I've got half an hour. Autonomous cars, still an open problem, although we've obviously made a lot of really good headway. You're seeing autonomous vehicles in San Francisco, in Arizona. Arizona. I haven't seen any in Florida, although since 2013, it's been legal. It is legal to drive a self-driving car in Florida. I think Pennsylvania, it's also legal. I think in Pittsburgh, they have self-driving cars. I don't think in New Jersey it's legal. I don't think it's illegal here yet. So that's why you're only seeing, you're certainly not going to see it in a place like New York for now. New York is crazy. Like, you have bikes and people and there's social norms and all these other things that are very different from other places. Some of the things that we've discovered is how hard this problem is, not just from the direct decisions that the models make about avoiding accidents, but the way in which autonomous systems interact with people. If you follow the rules in New York, stick to the speed limit, stop at a stop. First of all, you probably make no progress. And second, if you make progress, you can cause an accident getting the drivers around you alone. The other thing that has emerged is that when people interact with autonomous systems, with other people who are driving a system, they make eye contact. They look to see if you're looking at them. There's no person in the car. So like people do all these funny things and they tap the vehicle because they don't know how to interact with it. And the vehicle's gotten a lot better at doing this, but it's still an open area of research. Like, how do you get autonomous systems to interact with social creatures? How do you embed social norms, social interaction into an agent? It's not just about X, Y anymore. It's more like, well, X and sometimes Y. If I'm in New York, that mapping has these parameters. And if I'm in New Jersey, it has these parameters. And if I'm out in the desert, it has these parameters. Right? So we're getting to that subtlety. All of that is just built into humans. We kind of learned that. Some of us, anyway. I'm sure that people don't drive in New York. So what's on an autonomous car? GPS, LiDAR, or 3D cameras, maybe both. You have obstacle detection. You have some LiDAR systems. You have stereo cameras. Me and my students worked on a project. My lab is one of the branches of the work we do in my lab is thinking about the hybrid between, or the middle ground between fully autonomous and fully human driven. So we build these driver assist systems that basically try to make you not a bad driver. Which means that the agent has to figure out when is a good time to give you the instruction, how many times it should repeat the instruction, and whether you executed the instruction, and whether you executed it correctly. So is it correct? That's binary. How correct? 0 to 1. When? Well, lots of data. We didn't know how to program that effectively, so we got a bunch of data with asking people, is now a good time to interrupt you? And then we built a big model that learned that mapping. Okay. Cool. So there is a lot of ways to think about setting up this problem. Right? And one way is to give it the manual and say, follow the rules. The other way is maybe we learn from Sebastian and Stanley. We just have Sebastian and Stanley go ride their vehicle and record what they're doing, record any changes to the control parameters and how those are correlated to the terrain or to what they're viewing, and learn the policy from that, backtrack from the observations to a policy, and then see if you can mimic what they're doing, some average of what these two drivers are doing, or this generalizes to any K drivers. That's another approach. And again, very different from being like, oh, if sensor X is greater than 0.85, then blah, blah, blah. No. Just collect more samples. And therefore, now we have more experiences to draw from to provide to this model. And hopefully, if you have enough samples, and in almost all cases, this thing eventually converges. There's a cookbook, if you will, of going about training your model that tends to work. I can't think of a situation where I wasn't able to get X mapped to Y. Now, I also have never given it data where I didn't think there was a mapping from X to Y. I'm not like trying to predict the weather based on the color of my shoes. Although maybe there's information there. Like maybe, sorry, I'm like stream of consciousness, but think about it. If my shoes are wet, then maybe it's raining. And if I have enough examples where my shoes are wet and it's raining in the example, it might just look at it might also look at how like the intensity of light that's on my shoes. So like even there's might be a mapping from X to Y, right? It's really hard to find completely uncorrelated things. I mean, it's probably not hard to find, but you probably wouldn't be working on a machine learning problem that tries to discover that, right? So in other words, there is a process by which you think about the data that you need, collect as much of it as possible, think about the properties of that data, use those properties to inform the structure of your model, write the code that sucks in the data and maps to the output, and just let it run for days at a time and see if it converges. Hypothesis formulation is generating many models and just training them for days and looking and then ranking them over time. And then the final test is actually deploying it, which is called an out of sample test. That is the gold standard. That basically means, does it really work or did it only work on your data? The gold standard is always putting it out in the real world. 10 years ago, people were talking a lot about deep learning. I could change all of this deep learning stuff to generative AI or chat GPT or whatever. But people have been talking about ML in the news since you all were very young, very little kids. It hasn't, I would say, since the inflection point happened around 2010, when deep learning beat the deep learning based model won a competition for image classification. And so for decades, folks were writing image classification pipelines from scratch, programs with if else in it. And a team came out. I don't remember if it was, I think it may have been Jeff Hinton's team or something. He'd been working on deep learning for a long time. When I was an undergrad, my professors were saying, get away from neural nets. Neural nets are dead, they don't work. And almost everybody listened to him, except a few people who now have Turing Awards because they didn't listen to him. Jan LeCun, Jeff Hinton, Yoshua Bengio. I think those are the three who didn't stop working on this. I'm sure there were some others, but they were the ones who continued having impact. And anyway, so it's still in the news. All right, so deep learning is a particular kind of model. There's, for a long time in the community, we separated between shallow models and deep models, where deep models are these neural architectural based models, which you all sort of take for granted now, right? The shallow models are basically statistical models. And AI is a much broader field that includes logic and some other things, which are, symbolic reasoning and things like that, which might make a comeback, but for now, it's all deep learning based. The cool part about deep learning that differentiates it from shallow models is that when you have a shallow model, you have to design your features from scratch. You have to take an image of a cat and measure the pointiness of the cat's ears. So you have to go look for the pixels and do edge detection, and then you include that as a feature in your vector, and you do this for a bunch of features, and you do that by hand. And then you feed that into some statistical model, probably linear. AX plus BY plus CZ, where X, Y, and Z are your parameters or whatever, or the vectors and whatnot. And then you run regression or something. In deep networks, you say, nope, I just have X, and it's this lady, and her name is Anne, and that's it. That's all I know. I have a bunch of pictures of people's faces and their names. And I want you to learn whatever features you need to learn to make sure that when you see a picture of Anne, you can spit out her name. That's it. So I'm not designing the features anymore. I'm just designing the experiences, E, that I feed to the model, and the objective. The objective is that the output vector has to be a numerical representation of the name Anne. And I'm just going to pass in the raw image. All the pixel values in this matrix, that's a stack of, it's a 3-layered stack of a bunch of pixel values. Pixel values all being 1 byte, 0 to 255. That's all it is. Just 3 matrices stacked together, pass into this model. And if you have, a few tens of thousands of these, this neural architecture learns how to pull out meaningful features to map to that name. It's almost like magic, to be honest. It's still, I hate as an academic to call it magic, but it actually isn't well understood exactly why it works. What we know is how to put it together. We know that if you have this neural architecture and an activation function and backpropagation, and you link these things together so that information flows forward and backwards, and you have an objective function so that you know how to update the weights, which is what backpropagation is, that this thing tends to converge and tends to give you the right answer. But like, if I take out a node here, I don't quite know if the model will still work or not. I can't tell you a priori. It's an experimental science. Okay, but so what is the model doing? It turns out part of what has happened over the last decade or so is to try, there is a sub area of machine learning that's trying to understand what the deep models are actually doing. And so what we're seeing on the inputs are these pixel values, as I was mentioning, values between 0 and 255 in the structure of the matrix stacked in 3 because you have red, green, and blue. You're passing them in to this deep network. You're running CNNs. They're a particular kind of neural network which is extracting spatial correlations. And after it converges, if you study what the different layers are learning, you, for instance, would learn that layer 1 is picking out edges. Layer 2 has combined those edges in ways that you can pick out parts or objects. And layer 3 are different constructions of those objects following some structure based on the input data. So in other words, for a face, you get edges, facial parts, your eyes, your eyebrows, your mouth, your ears. And object models are, whether they're have a larger face, smaller face, long hair, short hair, bigger lips, smaller lips, et cetera, et cetera. Right? So it starts to combine them in ways that are constrained by the structure of a face, but within the variance of faces can pick out reasonable looking faces. Like by reasonable, I mean that looks human. I'm going to skip this one because I don't know what to say there. Next one. Okay, so then another thing that they tried was, all right, well, we see that this sort of generalizes for faces. If we increase the number of classes, we'll see a similar pattern. So it does turn out that you do get, it is this sort of bottom-up construction of the input distribution. You pass in an image, it first tears it apart and then puts it back together. Right? And so by the first few layers, you're starting to see edges, then you see parts of the object, then you start to see semblances of those objects, types of those objects, and all of those lead to the label. Okay, so the second layer were these shared features across all the objects, then shared object features, and then more specific features that are object specific. And now we have, you use YOLO. I don't know how many people here have used YOLO. So YOLO is an out-of-the-box object detection Python stack. And I don't know how many, they have several hundred objects that they can classify. They also have tracking and other capabilities, and they do it fairly fast. So again, this has been commoditized. You can just download it and run it on your laptop now. How many people have seen images like this where objects are labeled? Same kind of thing. YOLO gives you this. It used to be state of the art, had to be written in C++, could only run on certain machines, blah, 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 blah. I can run it on my phone. That has only been 10 years. Cool thing about deep learning. Again, getting into the sort of going deep on deep learning is going deep on deep learning. I mean, like really understanding what some of the properties of these models are. It's kind of interesting. So there's a paper that dates back from 2003, where they tried a deep learning approach that still works. So what you're seeing here are these input images with parts of the face covered. So they've zeroed out the pixel value on almost about half the face. And they've trained a model that has seen lots of faces where it wasn't zeroed out. And what they're asking the model to do is to reconstruct. They look at the last layer to see what it thinks the facial structure looks like. And you can see that it starts to fill in some of the face. And if you run this in iteration, you iteratively keep passing in the output back into the input, it keeps filling out more and more of the face, which suggests that the information about the facial structure is embedded in the model. You might be asking, embedded in the model, where is it embedded in the model? If we go back here, now we have these neurons, and they're connected by edges. Each of these edges have a weight that we're multiplying the input values by. And the process of learning is adjusting those weights. And that, if I were to take all of the weights and put them in one big vector, that represents the parameters of the model. The structure of the model consists of the nodes and edges and how they're connected. And the parameters of that model is this big weight vector. And that weight vector arrived at that particular configuration through this learning process. And so if you dig deep, the reason that it can reconstruct the face is because there's information embedded in that weight configuration and the structure of the model, such that when you combine it, it can infer missing values. It's already captured those correlations. So that's like a really powerful property of deep learning methods. And that's also why ChatGPT works. So the way GPT works is the same thing is based on this principle. It produced something that looked like language, and it keeps producing more by taking the output and passing it back to the input. And you're leveraging the internal knowledge encoded in the weights to produce more. This is the early forms of generative models. Speech recognition, again, we all kind of take it for granted now. This used to be what the pipeline looked like. I think for the most part, this is gone. And it's all a neural network. If you want to get it running on a Pi or something like that, you probably still need to do this part. This is the human feature extraction. It's called a spectrogram. There's different types of spectrograms. They're based on the structure of the ear. They pick out specific frequencies and generate an image for which we can run a CNN and then pass it to a decoder to generate what you're saying. So you can see how, like, as a building block, now you can go between writing a program, and in situations where it's really hard and unclear how to write the program, you fill in a machine learning model. Right? And then when you stitch those two pieces together, you have a composite ML system that solves your problem. So I've been just talking, any questions or like anything you've been wondering about or weren't so clear about? Yeah.
Under machine learning and AI used like really interchangeably, is there a difference between the two?
AI gets you more money. Machine learning is a subset of AI. AI is a very broad field. Most people who are working in AI are they're not even doing like broad machine learning or statistical learning. They're just doing deep learning. Right? And I would say that even amongst the people who are just doing deep learning, very few are designing new architectures. They're just downloading YOLO. That's what we're seeing. That's what I see a lot in like the real world. But yeah, so AI is like the umbrella term. And yes, you will see AI a lot because it gets a lot of clicks. And if you're raising money for your startup, call it AI and you'll get like 10 times more money. And like that, everyone's kind of we're all deep networks in some way. That's the objective function, like making more money. So we tend to do that. For me too, if I'm going off and getting a grant, I will call it AI. Okay, that's the thing now. Okay? Generative. You want to make money today? Call it generative AI. When you're just calling you're doing ChatGPT API calls. Get plenty of funding. No, but I'm being facetious, but it is actually true. And you kind of follow these terms But the reality, okay, independent of the money, talking just about the knowledge, AI is this broad term that does encompass all of those techniques. But very few people are like doing symbolic reasoning, right? Like generating symbols and equations and following logical rules. They're not really doing that anymore. All right, I'll skip this. Any other questions? Oh, shoot, we're almost done. All right. Types of learning. Roughly speaking, 4 types of learning: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. How many people know about these? So most of you, great. Okay, what's that simple one is this one. We know this. I've been talking about this the whole time. There's XY pairs, train a model. You're done. Unsupervised? What's an example of unsupervised learning for folks who know? Yeah. Clustering. Beautiful. Semi-supervised? Folks know what that is? So semi-supervised is, of course, some sort of mix between these two, where essentially you want to learn a bit of structure guided by your labels, and then propagate knowledge based on, closeness between the points. So like, oh, well, if this one is green, probably its closest K neighbors are also green. So I'll give them that. I'll give them that label. And reinforcement learning, we know what reinforcement learning is? Can someone give me a quick example? Yeah. Precisely. Very good. So I can go through these fairly quickly. Supervised learning, one version of it is regression. So there are these subtle things, subtle design choices that come into play when you pick a model. You're here, if we're doing regression and we're doing linear regression means it has to be linear, it has to be aligned. We can do, we can have it have more than 1, 2, 3 K degrees to sort of fit a curve around it, but we're making a hard choice about the structure of the data. When we're doing that, deep learning, of course, can fit lots of different shapes, a much broader set of shapes than just a line. In classification, this is where rather than take X and predict Y, according to the structure that we're learning, we'd like to predict a label. We want some function that approximates the likelihood that it will obtain a particular label. And we want that to be as close as possible to the ground truth. And so in this case, you might see that, having a linear separator may not work. You may need some kind of curve called sigmoid, and you'll do some logistic regression because of this logic function that you're fitting to this. And you can look that up. Okay. Of course, it can be multidimensional, tumor size and age, and you're looking for a linear separator. If you have when you're working with shallow models, SVMs are very powerful, right? And you pick a kernel a kernel is basically a transformation function that changes the relationship between your points, preferably into a projected space where there's a linear separator between those points. Sometimes that means you need to project into a higher dimensional space. Sometimes it means it goes into a lower dimensional space. Unsupervised clustering, right? And different clustering algorithms have different properties. So in the case of k-means, you're making a hard assumption by having a distance function that is, let's say, L2, the L2 norm, which is a standard distance function. Use L2 norm, then what you're saying is that the structure of your clusters are circular. There are other norms, like the L1 norm, where the structure is a little different. You can use Manhattan distance. It's very sensitive to the distance function that you define for feature vectors that characterize your objects. There's another form of much more complicated unsupervised learning, where you're clustering the genes based on some, I don't know, some property. Obviously, clustering is used in a lot of places. In fact, in sensing, we often have to rely on clustering because we don't have labels. Right, and so you can think about, one of the open problems in any one of these spaces is to collect a lot of data, do initial clustering, and then use the clusters to guide the labels that you get. And then maybe use semi-supervised learning, because I'm not going to ask an expert to label every sample in a cluster, but I want the most representative sample. And what might that be? If I have a cluster of points, what might be the most representative sample in that cluster? What do you think is the most representative sample? If I have a bunch of points, a point cloud. The sensor. Yep. And so then you start thinking, then you can think about like strategies for filling the rest in. The things at the edges, you're probably not, that might be another class. You're more likely as you move away from the sensor to be wrong. Right? And so you can randomly sample with starting with the thing that's closest to the sensor, the sample that's closest to the sensor, and then, judiciously pick points to get that, and then let everything else inherit the labels from the points that you're getting samples from. Independent component analysis. Again, there's an example of like separating voices in a room. A type of unsupervised learning, you're picking a basis function, and then you're doing some kind of decomposition such that, you can guess roughly how many people are talking. And you have to make an assumption about how many people are there. And then a lot of clustering algorithms, you have to specify how many clusters. Not all of them. But it gets complicated if there's always a parameter to tune. You might hear of clustering algorithms that don't require that you specify K, but you have to specify like density or something, or you have to specify some other parameter that dictates maybe an upper bound on how many clusters this thing can discover. So it's usually not very straightforward. Oh, another thing I wanted to mention before I finish the lecture, since I have to run, is okay, you can go through the rest of the slides, you can go and read about these other techniques. But I would say that the main takeaway when you're doing machine learning is that the ultimate oracle of whether you're right or wrong is a human. Please don't forget that. The first thing I hear from my students is, but the number is little. I'm like, yeah, but have you looked at the clusters? They don't make sense. I can't interpret this. This is completely meaningless to me. Please, please, please check with yourself and check with your lab mates and check with the community to make sure that the result is correct. It's only correct if it makes sense to us at some level. Maybe we don't understand layer 1, but when we get to layer N and make a final decision, that some human is like, yeah, that's the right thing. That's what we wanted. You didn't hit someone. Great. Okay. So, and it starts with very simple things, even with clustering. Oh, but the cluster structure is good. Yes, but why is a car in a cluster with birds like that? That doesn't make sense for our application to say that cars and birds are in the same cluster. You picked the wrong metric. You picked the wrong featureizer. I can always find noisy data that has an L2 distance, that has a linear separation between them. I can always do that. Give me 2 random vectors, literally random, and I'll tell you their distance. And if they're close, I'll say that they're in the same cluster, but they're meaningless. So the math is supposed to resonate with our experience of reality. And if it doesn't, it's probably wrong. All right, that's my takeaway. So hope you enjoyed this high-level discussion and enjoy your summer internships. I hope they are filled with machine learning problems and productive. All right, thanks.